Okay, hello everyone. So we're gonna just go over this question here that we were going over during the review session. Sorry for this late video, but here we go. So hopefully this is helpful. So the question that we were going over in the review session on Thursday was and this question for everybody joining us is for analytical chemistry course, second year analytical chemistry course, but the question we were going over on Thursday was a new method of mercury determination in water results in a linear calibration curve. So what's a linear calibration curve? So when we're measuring a sample using an instrument, we always want to, or usually in most cases want to use a linear calibration curve or develop a linear calibration curve, because when we analyze something through an instrument, it's not going to give you, oh, you have 10 millimolars of potassium or 5 millimolars of whatever, mercury, for example, right? It's actually going to just give you a signal. And so that signal could be absorbance, it could be a current, it could be intensity, it could be different things. But it will be a signal, and we need to correlate that signal with concentration. So usually what we would do is we would make, let's say, these are your volumetric flasks, right? Usually we would do at least 5 points. So you'd make different solutions of, let's say, 1 millimolar, 5 millimolar, 10 millimolar, 20 millimolar, and let's say 50 millimolar, oh, no space, but 50 millimolar of our standard solutions, and we would run those through our instrument and we would get different points, right? Usually it's not pretty, so that's why I didn't want to make it a straight line, but we'll get different points at these different concentrations. So obviously this is not to scale, but alright, so we have these different points of concentration, and by the way, the x-axis is concentration, so we'll call this concentration of mercury, just for the sake of the question. But yeah, 50 millimolar, right? So I mean, this is not, I'm drawing this live, so this is not like pretty or anything, but we would usually make these curves and we would plot these concentrations with respect to the signal that we get from the instrument, and we would get this line of best fit, which is a calibration curve. And so this calibration curve has an equation of the line of y is equal to 0.207 plus minus 0.001 x plus 0.008 plus minus 0.006. Okay, so that's the equation of the line for this linear plot that we developed with our standard solutions, or our calibration plot. And so y is the measured response, right, the signal, and x is the concentration of mercury. And the values in the parentheses, so these values here, so I'll underline them in, let's say, red. These values here are your standard deviations for the slope and the intercept, right? And so from this data, what we want to calculate is the limit of detection, LOD, and the limit of quantification, LOQ. So let's talk about these two things first, okay? So let's talk about limit of detection, and then limit of quantification will be a little bit easier to discuss. So this is a different graph, so I'll actually use a different color as well. So let's say we're running an absorbance spectrum, right? So an absorbance spectrum where we're measuring the absorbance at all wavelengths, and so you'll do this sometimes in the case where you don't know the absorbance of your analyte and you want to detect the absorbance of your analyte versus absorbance. And so sometimes you'll get something like this where there's a lot of noise, and then at a particular wavelength we get some sort of absorbance, and then we continue with the noise, okay? And so our analyte of interest absorbs at this wavelength. And so, but how do we know that it's exactly our analyte of interest absorbing at this wavelength, and how do we know if this is a signal or if this is just a part of the baseline? Because sometimes if the baseline is like this, you could imagine that I could get something like this, and I'm going to be in question, oh, is that a signal or is that just a part of the noise of the baseline, right? So the limit of detection is the minimum concentration of your analyte needed to say that you the minimum concentration of your analyte in which you could say that you can actually detect your analyte. Okay, so what do I mean by this? So in this absorbance spectrum, I could always extrapolate this baseline like this, right? And so the idea is that the limit of detection should be the signal that you get should be no less than 3 times more than the baseline, than this baseline, in terms of the magnitude of the absorbance. If the signal that you get is less than 3 times the baseline, then that means you cannot say that you accurately detected something. If the signal that you get is more than 3 times your baseline, then you could say you can say that you can say accurately whether you detect something or not. Okay, so I'm just gonna delete this part here really quickly, and so the equation for limit of detection, it depends on the textbook. Sometimes it'll just be a 3, sometimes it'll be a 3.3. Doesn't matter, just use whatever is used in your course, times the standard deviation, and we'll talk about the standard deviation in a second, over the slope of your calibration plot. Now, for the limit of quantification, it's the same thing. It's the minimum concentration in which you could say that you can quantify your analyte. So the difference between limit of detection and limit of quantification is that limit of detection, it's just a yes or no answer. Either your analyte is, you could say either your analyte is there or it's not there, but you can't say that you can't quantify how much of your analyte is. With limit of quantification, it's not a yes or no question. It's you could the minimum limit above which the minimum concentration above which you can actually quantify and say, oh, I have X concentration of my analyte. I have 10 millimolars of mercury, whatever. So above, if it's above that, if the concentration of your analyte is above that limit, you could actually say how much of your analyte is in there. And so, but the criteria is a little bit higher for quantification, as you can imagine. So the criteria for quantification is actually 10 times the signal from your baseline. If the signal that you get is more than 10 times the signal from your baseline, then you can say that you can quantify your analyte. And the equation, it's very simple, similar to the LOD, except it's 10 times the standard deviation over the slope. Okay, so it's a higher bar to reach for you to quantify something versus for you to detect something, right? And so we'll just outline these two variables here again. So this is the standard deviation of blank, and we'll talk about that in a second. And this is the slope of calibration plot. I'll just say CP. Okay, so it's the standard deviation of your blank. Usually what we'll do is when we do the blank measurement, we'll do it 3 times and we'll get a standard deviation, and so it's usually that standard deviation. However, you weren't given that information in this question. All you're given is an equation of the line. However, what's a blank? A blank is something that has everything except our analyte. So our analyte is at 0 concentration. And so if I extrapolate this line to the point where I have 0 concentration, or where the x is 0, then I can figure out the signal that I get from the blank. Let's say if it was an absorbance, the absorbance that I get from the blank, and I could get the standard deviation, right? And that's really simple. I just need to set x is equal to 0. So if x is equal to 0, then y is equal to 0.008 plus minus 0.006. And my standard deviation that I'm looking for, all right, we'll do a different color, is right here, right? So for limit of detection, and I need to do this quickly because I have an NFL game, London game to watch, but for limit of detection, it'll be 3.3 or 3, just use whatever is used in your lectures, times the standard deviation at the x-intercept, which is 0.006, over the slope of the line, which is 0.207. And that's going to give me, one second, I have my value recorded here. It will be 0.0869. Now the only issue is the limit of detection should always be in units of concentration, and the question doesn't give me what units of concentration the equation of the line is given in, so it could be in micromolar, it could be in molar, it could be in millimolar. So it should be some type of molar, either micro or milli, I don't know, but there should be the units of either micromolar or millimolar when you're reporting the limit of detection. Okay, and then the limit of quantification is very similar, right? It's just going to be 10 times 0.006 over 0.207, which is equal to 0.06 over 0.207, and that will be, so oh, sorry, by the way, for this question, actually, the way I did my calculation, I actually did it with just a 3. So again, just look at the number that's given in your lectures. It does differ a little bit depending on who's teaching it, but it's either going to be a 3 or a 3.2. You just adjust the equation based on that. And so I actually did not calculate this one beforehand, but it will be 0.290 whatever molar, either micromolar, millimolar, picomolar, whatever. And so that is the answer for this question. Those are the 2 answers for these questions. I hope this helps with your midterm. Sorry for the answer for being a little bit late. I just got a little bit busy during the weekend, but good luck with your midterm. I hope you all do well, and I will see you in the labs next Thursday. Yeah, Thursday. Okay, bye.